Good morning, my dear friends. See now, we'll take up another problem in the shear chapter. I will read this. A PSC beam 250 mm by 1000 mm. Okay, here it is now 250 mm by 1000 mm is subjected to a shear of 4,20,000 Newton at a section under working loads. Okay, in sense shear force he has given. The effective pre-stress in the tendon is 7,50,000 okay newtons. Okay, he has given the effective pre-stress, which is inclined at an angle of 10 degree with the horizontal at the section. Am I right? The cable is now inclined at 10 degree, okay, with the horizontal. The normal stress on the section under working load is 12 Newton per mm square compression at the top and 0 at the bottom. In the stress distribution he has given. The allowable principal tension in the concrete is 0.8 Newton per mm square. In the sense, he has given the allowable principal tension or the permissible principal tension, okay, as 0.8 Newton per mm square. Estimate the principal tension at the centroid. In the sense, at CGC, you are supposed to find out the principal tension, okay, and comment on the necessity of shear reinforcement, okay, in sense whether shear reinforcements are required or not, you have to tell. Assume Fy is equal to 250 Newton per mm square. Use elastic method, okay. So now problem is easy. I think I will take you through this. Now area of concrete can be now easily calculated. Area 250 by 1000 will give me. Moment of inertia can also be easily calculated. BD cube by 12. Okay, Baba, shear force is now given to you. Phi is so much. Okay, and the precessing force is 75,000 newtons. Okay, theta is 10 degree, as you know. Okay, so but now shear force in concrete can be now easily calculated. VC, it is V minus P sin theta. Am I right now? Since cable is laid at some inclination, okay, your cable also will carry some shear force. So 42,000 is your V minus P. P I know, it's here. Theta is 10. So now your shear force carried by the concrete is 289,764 newtons. Okay. Now, Papa, as usual, since it is a symmetrical section, I want to consider the element at the centroid CGC. Okay, I think tau V can be now easily calculated. It is 3 by 2 VC by BD. Okay, otherwise you can use your own general formula. Since it is a rectangular section, this equation is okay. Okay, so your tau V works out to be 1.738 Newton per mm square. Okay, also, Baba, at center, I want to calculate sigma x. Sigma x can be now easily calculated. It is F by A. F I know, area I know. So I can easily calculate the sigma x value. Okay. And since vertical precessing is absent, sigma y can be taken to be equal to 0. Okay. So now with all these things, I can calculate the principal tensile stress FCT. FCT is given by sigma x plus sigma y by 2 minus under root of this much. So now all the values are known to you. So you can find out the value of FCT. FCT works out to be minus 0.79 Newton per mm square. Okay. See now, this is our principal tensile stress. Okay. Now what he says, in the problem, he says that the allowable principal tension is 0.8. Am I right, sir? No. The allowable principal tension is 0.8. But since your existing principal tension is less than your allowable principal tension, I say that the beam is safe in shear. The beam is safe in shear. Am I right now? Because your existing shear stress, existing principal tension is less than permissible principal tension. Am I right now? So I can say that the beam is safe in shear. But Baba, your IS code doesn't allow you like that. What it says is now minimum reinforcements, minimum shear reinforcement have to be placed. That's what it says. Your IS code, according to IS 1343 1980, okay, minimum shear reinforcements are required. And how to design those minimum shear reinforcement, Baba? It is through this equation. Your IS code gives on page number 48 this equation. ASV by BSV equal to 0.4 divided by 0.87 Fy. Okay, this is the equation. So now, what is this ASV? Okay, B is your breadth. SV means it is a spacing. 0.4 is 0.4, 0.87 is 0.87. Fy is, it is the characteristic strength of the stirrups he has given in the problem. Okay, ASV means it is the area of stirrups. If it is two-legged, it should be into 2. If it is three-legged, into 3, etc., etc. Okay, so now we shall use 6 mm 5 two-legged vertical stirrups now. Okay, so now ASV can be now easily calculated. Pi by 4 into 6 square, because I am using 6 mm 5 wires, into 2 because it is two-legged. Okay, so ASV is this much. Breadth of the beam is 250 mm and Fy value is now 250. So I can easily calculate the spacing of 6 mm 5 two-legged vertical stirrups. So in this equation, spacing can be now easily calculated. But rearrange the term and you will get this equation. Yes, spacing SV is equal to, it is so much. But you need not remember this equation. It is there on page number 48. Okay, so now spacing works out to be 128 mm center to center. Okay, this is how we can calculate the spacing or design the shear reinforcements in the PSC. Sometimes in the examination, they may ask you to use IS code, or there is something called Guyon's method. Okay, in sense, whenever you want to calculate the nominal stirrups, okay, nominal shear reinforcements, this Guyon's method can also be used. Okay, so what exactly this Guyon's method says, we'll try to, in a sense, we'll try to solve the same problem by using Guyon's method. Okay, so whatever Guyon says is, see now, according to Guyon, the spacing SV can be calculated by one equation, Z cot phi ASV Fs by Vc. This is the equation by which I can calculate the spacing according to Guyon. Okay, where Z means, Z is I by Ay bar. I think I also you know, Ay bar also you know. Okay, phi means cot phi. Phi means angle of slope of possible crack. Okay, phi. And see now, the values here he has given one table according to Guyon. This table can be now referred. If principal tensile stress, if FCT is less than FC allowable by 20, then tan phi value can be taken as so much and Fs value can be taken as so much. If FCT is greater than FC allowable by 20, tan phi can be taken as so much and Fs can be taken as so much. If this is the case, if tau c is greater than sigma x by 2, then tan phi can be taken as 1 and Fs can be taken as 140. Okay, see now I will assume again this thing now. Okay, see now we will try to calculate this thing now. But Ay bar I know already, Ay bar. Z is equal to I by Ay bar. Am I right now? In sense, just now you have seen Z can be written as I by Ay bar. So I will try to calculate this Z value is now here. Now I want to calculate a term called FC allowable by 20. Here is, you know, in this table it is there. FC allowable by 20. FC allowable is 0.8. It is given in the problem, divided by 20. It will give me 0.04. And how much is your FCT? The principal tensile stress worked out is 0.79. Am I right now? So now you will see that your FCT is greater than FC allowable by 20. Am I right now? FCT is greater than this value. Is it or not now? In the sense, FCT is greater than FC allowable by 20. In the sense, you lie in this case. FCT is greater than FC allowable by 20. But at that time, tan phi can be taken as 2 tau v by sigma x and Fs can be taken as 140. Okay. So now, tan phi is equal to 2 tau v by sigma x. Tau v I know, sigma x I know. It is so much. Then tan phi is, excuse me, okay, FSC is 140 mm. Okay, sir, now, and tan phi is so much now. Therefore, phi can be now easily calculated. Therefore, I want cot phi, because in the equation, cot phi is there now. Okay, I want cot phi. Cot phi value is so much. And Fs from the table, it is 140. Okay. Also, as you know, Bano, ASV we have already calculated 56.55, and VC also we know. So now spacing can be now easily calculated SV by using Guyon's equation. Okay, this is what, if you fill all the values, you will get the spacing. This is how now Guyon's method can also be used to find out the spacing. Okay, thank you very much.